So yeah, the agenda today is going to be how we need accurate integrated field transient modeling and how that can improve HIPPS design. We're going to see the interplay between the nuances we require for accurately modeling slugging, which is a transient multi-phase flow phenomena, and how that relates to accurate transient behaviors that need to be captured for HIPPS design, which is a high integrity pressure protection system. So we'll start with a HIPPS overview, understanding what a HIPPS is and why we will need a HIPPS in certain conditions, and what are the design challenges for accurately and efficiently choosing your high integrity pressure protection system. Then we'll look at slugging, and noticeably we're going to focus on severe slugging. We're going to discuss modeling of slugging and why we really require the compressibility to get accurate slugging behavior, and that's the overall system compressibility. Then we'll discuss near wellbore dynamics. We're going to show how the near wellbore adds mobility and compressibility, which are analogous terms to what we do in multi-phase or transient multi-phase flow in Olga. We're going to see how a near wellbore model will behave with bottom hole pressure oscillations, and discuss why a near wellbore model is key for HIPPS design and for things like slug modeling. And that's going to be basically it. We're going to conclude and make sure the message went through, and we'll have some time for questions and answers. Okay. So HIPPS overview. So what's the purpose of a HIPPS? So typically what happens is we end up having a legacy asset which has been operated with easy to tap reserves, which for instance tend to be in shallow, large reservoir which have low shut-in pressures, okay? But you might have much deeper into your, below your mud line, another previously marginal reserve, which could be of higher pressure. So you have really two options to design this. One is because the previous reserves you had a much lower shut-in pressure, your legacy asset is not rated to take in new reserves that come from deeper formations or from abnormally high pressure formations, and therefore it needs some sort of a pressure protection, or you would require a completely different set of risers and pipelines or subsurface facilities to bring that production topside while protecting your integrity, okay? And therefore, the HIPPS comes in as a protective layer which allows you to greatly reduce the CapEx footprint, okay? So if you see here on the left, we have that scenario where we are using a HIPPS. So the red would be the new production system or new production equipment which needs to be installed to protect the integrity of your existing facility. And the left side would be the amount of new equipment is much smaller than what you would require if you have no HIPPS. You would need an entire new riser, which tend to be expensive, and some subsea flow line connecting to that high pressure wellhead. And basically you wouldn't be leveraging the existing asset, which may already be depleted and could actually have available real estate to create synergy. So sometimes the only economical way to bring these fairly marginal new high pressure production would be to install a smaller capital footprint equipment, which is a HIPPS, compared to an entire riser and subsea flow line rated at much higher pressure. Okay. And what are the challenges? So the first thing is you want to make sure that it's technically feasible. So whatever requirements you come up with, which we're going to see later in the presentation, you need to make sure that you have already equipment that can behave in that manner you require. For instance, the speed of the closing time is key. Okay. But there are many other nuances, much more complex, but that's basically the founding principle is how fast do I need this set of HIPPS or valves to slam shut whenever I have an overpressure risk, okay? And you also need to have operational flexibility because you don't want to be operating too near to the HIPPS trip point that you're going to have spurious trip every time. So it really, not every field is suited for a HIPPS because it just may not be technically feasible. And then the second challenge would be the cost. So we want to optimize the cost of these HIPPS. So you have a very real need for safety, and there's a technical need for a robust design, but that can increase the cost of your HIPPS. And there are substantial cost changes if you, for instance, need a valve that reliably closes within 90 or 60 seconds against 15 seconds. So, that's a bit of the introduction of what's the HIPPS and what are the challenges that we consider when looking at this issue. So another schematic of what we just saw previously. Again, we have a second formation that's coming online later into a brownfield. This is a typical scenario where upstream HIPPS are required. You would install a HIPPS. So you would have a high pressure wellbore, the HIPPS system, and then a fortified segment at higher pressure. And you're going to be leveraging the existing low MAOP production facility, okay? So we just need to protect the low pressure production system, okay? And the analysis that we typically do is a transient pressure buildup. And there are two scenarios, and because in the interest of time, we're going to cover one of them. So the two scenarios that typically size a HIPPS under the conditions I just described here, which is an upstream HIPPS, is that you have a transient pressure buildup after you suddenly block the flow. Let's say there's an unexpected valve closure topsides or an issue subsea. Maybe you also have an MOV subsea in the manifold or even a flow assurance blockage. So you unexpectedly shut production, and then you're going to pack with high pressure fluid your production system. And then you have a transient pressure buildup into your production system. The second sizing scenario is going to be you have an accidental restart into a block system, so everything is closed, and suddenly you open the wellbore when you shouldn't have opened it. And that can also be a sizing criteria. But let's discuss again, like I said, about the transient pressure buildup after a sudden peak flow blockage. So on the x-axis here, we have the time. On the y-axis, we have the pressure. And we're going to be looking at what happens basically at the spec break location with pressure. So initially, we're operating normally at peak production, early life, maybe even month zero of the expected new production from the high pressure well. And then suddenly a blockage occurs that wasn't planned. So what's going to happen is you're going to continue packing high pressure fluid into your low MAOP system, okay? At some point, the pressure will reach the critical point that's a HIPPS trip point, which you have designed your HIPPS to start slam shutting as soon as you see or you detect this pressure, okay? The HIPPS will start tripping, and then the HIPPS should complete its trip or its entire reaction and travel time should be completed within the time that it would take to continue to pack all the way to the MAOP. And then let's assume you have a HIPPS that work properly. So your pressure your pressure into the low MAOP segment will never go above the MAOP. On the other hand, if you had no HIPPS, you would have gone above the MAOP and you would have a risk of integrity compromise, even catastrophic failure, depending on how much the difference is. Okay, so basically the outcome of these studies is to establish that technical feasibility. Is this reasonable, what we're saying? Do we have enough margin between the required trip time and the expected operating conditions? And then, is this travel time reasonable, and do we have reliable equipment and economical equipment that we can actually use? Okay, and another issue would be also determining the fortified zone segment. But today we're going to be focusing on the transient blockage during peak production after suddenly and unexpectedly. Okay. So the tricky part is having a transient multi-phase model that allows you to get the proper pressure buildup. So the devil is in the detail, and here it is. Basically, we really need to get an accurate pressure buildup response. Okay. So again, just repeating myself a little bit. There's two major things. You have cost considerations. If you have a too onerous design, maybe a too large or a fortification zone or a too fast acting, it's going to increase your cost. If you don't fortify enough or it's too slow, you risk catastrophic failure. In reality, you probably risk to not get your permit approved by the regulator. Okay, but these would be what's competing into the cost consideration of a HIPPS. And then you really want to have an accurate model and modeling so that you can effectively size your HIPPS, which is safe enough yet not too onerous. Okay. And that really requires accurate transient multi-phase flow modeling, and that's integrating the reservoir all the way to the top sides, and we will be discussing that in the next slides. Okay, so a bit of a shift change, going to severe slugging, and you'll see how these two concepts that are seemingly a bit away from each other are actually quite related. So this is going to be discussing severe slugging. So you have hydrodynamic slugging, or you have terrain or severe slugging. Here we're discussing terrain or severe slugging. Okay. So basically, the concept is that should you have a blockage at the riser base, and that can happen at low fluid number, you may have a hydraulic blockage. You're still going to get production coming in from your wells. This is during continuous operation. So you will have a rate of pressure increase in the pipeline, and then you also have a rate of pressure increase on the riser. And depending on how fast your liquid column rises and on how fast your pipeline packs, you may or may not be stable. So whenever we compare this imaginary pressure increase on the pipeline given a certain blockage at the riser base against the imaginary pressure increase on the riser given the liquid column segregated and growing at the production rate, whenever those two are equal, you're at the boundary of stability. And this is the Boy criterion. It has been discussed extensively in the literature, but I want just to call your attention to that DPDT pipeline. It basically plays into the compressibility of the subsea. In this case, if it's subsea, this is a riser, right? The subsea pipeline or the subsea piping compressibility plays a major role on the stability, okay? So now let's look at the Boy criterion, okay? This is a specific scenario, a numerical experiment, if you will. So here, what was done was basically injecting multi-phase flow through around 400 meters of slightly uphill piping. Then we have a downcomer, again, slightly downhill. And then we have a riser flowing to a 50 bar outlet pressure. And you notice there is also a dead leg. And this dead leg right here, nothing is going through it. So on steady state, it shouldn't have any impact on the behavior of the system. But basically, that means that whatever you do with this flow, it's going to impact the pressure you observe at the inlet, yet the dead leg shouldn't matter in a stable, steady state flow. So what you see here is going to be the inlet pressure, so the pressure at the multi-phase injection, and that's for a specific flow rate. In this case, and again, it's not important, these are not very typical units, kilograms per second. What matters is at a specific constant flow rate, multi-phase flow rate, which is the same for each of the simulation results you're going to see. The only changing parameter was the dead leg diameter, basically how much volume we have there, or again, the compressibility of that subsea piping. So when we use a diameter of 1, I believe in this case is 1 inch, we didn't have any pressure fluctuation. And you can see the pressure was around 735 psi. Now we go to the 2 inch, you can see that the color changed from mustard to gray. Nothing is happening. We keep increasing the dead leg diameter. Again, nothing. 8 inch, 16 inch, nothing. And then 32 inch, suddenly we start to see some instabilities. And then if the dead leg, the 400 meter dead leg goes to 64 inches, sure enough, you start seeing slugging. And this is the terrain type or the severe type. I mean, you might differ of how you define severe, but this is an overall system transient instability. It's not related to the flow pattern only. It has to do with the interaction of the entire transient multi-phase system. Okay, so just to recap here, small dead leg, low compressibility, no slugging, huge dead leg, large compressibility, severe slugging. Okay, so this is going to be the recurring theme, like what's impacting the compressibility of my production system. So another bit of a shift change. Now let's go to the near wellbore. So the near wellbore, if you think about it, is basically a big lung or breathing lung, which can expand and contract. That's basically the mechanism for primary recovery. It's the expansion of the reservoir fluid into your wellbore. So if you solve for this diffusivity equation, which is, it has a fair amount of assumptions that you have a cylindrical wellbore, homogeneous, single phase, and whatnot. If you solve for this specific partial differential equation and focusing on this ratio here, which is the mobility, 1 over the mobility, basically the permeability K, the fluid viscosity mu, the porosity of your reservoir phi, and the compressibility C. And we overimpose this behavior with an oscillating boundary condition, okay? Here, again, the units are not really important. What I want to show is that if you use currently in our state-of-the-art transient multi-phase simulators, it's very common to use a simplified IPR, which is a productivity index, really, which is a linear trend with the flow rate. If you solve the simplified IPR, basically you ignore this equation and use our current method, you would obtain this red oscillating behavior, which I'm following with my cursor right now. But in reality, because the reservoir has low mobility, which can be a high compressibility or a low permeability or a combination of both, a low mobility reservoir will result in much wider flow rate fluctuations to the same bottom hole pressure condition than if you just assume the simplified IPR that we currently use in our state-of-the-art transient multi-phase simulator. So in a sense, we're using a very complex state-of-the-art transient multi-phase flow simulator for the wellbore and pipeline, and we're really using something that's 70 years old for the inflow behavior. And so it turns out that at high mobility with very high permeability or very low compressibility, you end up with roughly the same behavior. So on many conditions, this assumption that we use currently in our everyday simulations in flow assurance might be okay, but under certain conditions, they are definitely not okay. You're neglecting the entire compressibility of the rock connected to your wellbore. Okay, so looking at it, basically we have the low mobility increase the inflow sensitivity. If you can think about it, let's discuss whenever the permeability is very, very low. If that happens, the flow rate is just the slope of the pressure gradient times that permeability and the wellbore area. So with a very low permeability, you might have a steep reservoir wellbore radial pressure profile. So at steady state number one, you would have a flow going into the left direction, right? The slope is coming here, so the flow is like going this way. If you have a sudden bottom hole pressure increase, in reality, you might have backflow into your formation. And then after enough time has passed, you then have a third steady state condition, which you will still have production going to the left into the wellbore. So radius equals 0 is into the well, radius infinity is far away from the well. Okay. So that being said, in a real case, not necessarily a very low mobility case, you still have this sort of behavior where you imagine you're coming from steady state 1 in black, you have a specific flow rate into the wellbore, and then you have a sudden bottom hole pressure change. So you'll have a steady state 2 in blue after a long enough time of applying that boundary condition. But in between, you will have a transition state here represented in red, which will have a much lower flow rate. You see the lower slope than the final steady state. So our current tools just consider the blue and the black curves. That's the steady state IPR approach, the conventional approach we are currently using. And it completely neglects the intermediate state, which is the transition. It's basically like temperature-wise analogous of using fast wall instead of using wall. Sometimes it's okay, and sometimes it's not. So yeah, what I just mentioned. And how will this look like in reality? So in reality, you would have a steady state 1 at high production rate. Suddenly you increase the bottom hole pressure, you will have an undershoot, and then you'll stabilize to a steady state 2. And if you apply this to the tool we use in Olga currently, or in our state-of-the-art transient multi-phase flow, you would just get a step change, and you wouldn't see any undershoot nor any compressible behavior of that reservoir connected to the wellbore. And again, bringing you back to that compressibility concept, which is key for accurate transient multi-phase modeling, okay? And this type of data can be available from well test. It can also be inferred from your PI, your productivity index data, and the entire recovery and the recovery mode. So this is information that's readily available and not really ambiguous, okay? So, and now going back to the HIPPS, remember we're discussing the sudden blockage into a peak flowing system, right? So we are flowing at peak rate, and suddenly we unexpectedly block the outlet of this production. We pack the system. So that would be analogous to a well shut in. So what you would see in Olga would be a very fast pressure response. And the real response that would actually be a bit of a slower increase that eventually converges to that maximum shut-in pressure, but it would be, less onerous. Okay, so that's going to be the next part of it. So just credits to a paper, and actually a researcher that made a few papers about this. This is Pulcinato Garcia. He proposed in 2014 a dynamic IPR. It's actually an analytical solution to have an IPR that accounts for the transient changes in your reservoir. So, but what I thought was really insightful from that paper is here you can see the flowing bottom hole pressure for a well bore with a transient multi-phase flow simulator, where he neglects the compressibility of the reservoir using basically what we use currently in our state-of-the-art transient simulators, which is a steady-state IPR. He has a constant bottom hole pressure. Yet when he applies the dynamic IPR, which has the same steady-state behavior as the blue curve, he was able to capture well loading or well heading, loading and unloading. Okay, so this is severe slugging, or analogous to severe slugging for the well bores. Okay, so this is the bottom hole pressure. This would be the wellhead pressure. So this has been observed. This is known to artificial lift people. And it's basically a phenomena we're neglecting into our flow assurance simulations, okay? So this also was one of the reasons the RockX paper came up. They also, RockX was one of the options to connect Olga to a near wellbore reservoir model. And it also showed quite different transient behaviors when comparing with and without the reservoir dynamics. Okay, so this is not necessarily a new concept, but it's something that's fairly tricky to get right. Okay, and again, if you want to get the right pressure build-up response, which was key for slugging, and you can see here how it makes a big difference. Having the wrong pressure response tells you have no slugging when you would actually have a lot of slugging. So getting that pressure build-up response is key. Okay. So the conclusion here is we have a pressure build-up rate and near wellbore modeling. Okay, and that impacts the HIPPS design. So if we build HIPPS based on the current approach, which neglects the near wellbore dynamics here on the left side, what we get is, again, we're flowing at normal operating pressure. We have an unexpected shut-in, and the well keeps packing high pressure fluid into the system. You have the pressure build up. You go to the HIPPS trip point, and then the HIPPS trip start, then initiates, right? It completes, it protects your system. Now, on the right side, if you consider the near wellbore dynamic, what we're postulating is, well, you will have the same behavior now. However, you're going to have a much slower pressure buildup. And then when you compare these two designs, here you have on required HIPPS trip time, and on green, the required HIPPS trip time when you consider the near wellbore dynamic, which is our approach as EVOLEAP. You may have a large difference into the required HIPPS trip points, and one is more realistic than the other, actually. So the difference in these HIPPS trip can impact the overall HIPPS success. A slower HIPPS may be technically feasible. Maybe you can actually increase your HIPPS trip point, which is far enough from your normal operating conditions, such that you will not have spurious trips. Maybe you instead of needing a valve that closes in 2 seconds, which is miles away from your platform, you might need a valve that closes over a minute or so. So it can greatly reduce the cost and the constraints on the design. And it can even if you don't use it for these two above, I've also seen in HIPPS projects that there's some regulation hurdle. It can also be used to basically argue the design that was done is extremely conservative by presenting the results of the two approaches. Okay, so let's talk about proof of this. All of it has been quite conceptual, but at Evolib we developed a near wellbore transient tool, a fairly complex tool, which is directly included into Olga. And we're going to be modeling a accidental blockage topsides, okay, during peak flow production. We flow at peak flow production for an hour, and the well continues to flow. We shut in, and then the pressure builds up, okay? So I want you to understand the results you're going to see have exactly the same Olga model. So the wellbore, the tubing, the riser, the piping, everything is identical. It has the same steady state flowing pressures and temperatures, okay? And also, of course, the same flow rates, okay? However, one simulation used the conventional IPR model, and the other simulation uses our more realistic transient near wellbore model, which considers the compressibility of the reservoir. So what you have here is our actual data from our simulations, and you have here the riser pressure. You're observing, let's say, pressure here, which is a segment that's rated only for ANSI 1500, okay? So you have flow for about an hour, which is 3,600 seconds. You create that accidental blockage, so pressure starts to build up, and you can see how basically the blue, which is what you get with the Olga near wellbore model, which is our method, builds up pressure much more gradually than if you use the conventional IPR method, which assumes instantaneous response to the flow change, okay? So just making, you have here the HIPPS trip point. So basically for the gray scenario, you would need a HIPPS that trips from the time it takes to from the gray to get from here to here, right? And on the blue one, it's a bit different. This is just the same results, but zoomed in. So at the closure initiation, which is at 1 hour, we're looking at the pressure trends. So the required HIPPS trip time is roughly 45 seconds if you consider our conventional approach, but the real time that you would need to really build up pressure all the way to that ANSI 1500 is more like 45 minutes, okay? So this can be a major difference in terms of feasibility and cost for designing your HIPPS. Okay, I hope this was clear. So again, key takeaways is HIPPS are trending, and they are really useful to unlock reserves that would be otherwise less economical or even not recoverable in an economical way. It really allows you to reduce costs. Okay, then you really need accurate modeling to select the HIPPS to determine its feasibility. Okay, and then the near wellbore dynamics matter a lot to get the right transient behavior, including even severe slugs, which is a seemingly unrelated topic, but it's actually not. And the HIPPS project efficiency actually can be greatly improved if you do consider an accurate integrated model as we're proposing here at Evolib. So that's pretty much it, and I'm open for question and answers.
Thank you, David, for taking us through the handshake that needs to happen between the reservoir and hydraulic dynamics to make HIPPS systems both safe and cost effective. We have some questions that have been posted. So let's move to the Q&A portion of the webinar.
Sure.
Okay, first question is, how do we know that this approach is more accurate for HIPPS design?
Well, that's a good question. So it's basically something that goes back to the concept. We know that when we have a shut-in, the wellbore will take a while to build up pressure, and there's actually pressure build-up test as well test. And even working, I've worked with production data, and you can see whenever a wellbore is shut in, it can take sometimes even weeks to build up pressure all the way to the maximum shut-in pressure. So this is something that's known, but has been a bit neglected because it's fairly complex, and there are no, in my opinion, this is again part of my opinion, but I think there are no easy to use tools which properly merge the two dynamics, the near wellbore with the wellbore itself. So it by definition is more accurate, and it's been known since the beginning of well test theory that you really take a while to build up pressure when you shut in a well. Okay.
Thank you. Another question is, what if the sizing case is not the accidental blockage during peak production?
So if during peak production, okay, so there might be other sizing cases such as an accidental restart into a blocked system. And sometimes that can be the sizing effect. So again, it might change the result, meaning that it's unclear how the near wellbore would affect those scenarios. It's something we haven't yet checked. But at the same time, we still believe that this, including the compressibility of the near wellbore, will improve the accuracy of the model. So if the specific sizing condition is the accidental blockage, accounting for the near wellbore is actually a bit less conservative, although more accurate, which can give you design margin, but it might move the needle in other ways if the sizing case for the HIPPS is another. So that's not clear yet, and it would be an interesting thing to explore. This is a fairly new tool we've developed. Okay.
Good. Again, I invite you to post any questions you have in the Q&A side of the panel. We do have another question. Why change the current method if the current method is more conservative?
Yeah, I mean, that's been a bit addressed during the presentation, and it's true that the current method for the accidental blockage during peak production it seems more conservative because it results in less travel time allowed for the HIPPS, but it can be unnecessarily conservative, and you might be leaving behind reserves that could otherwise be recuperated because you actually have much longer than you think, and then the HIPPS suddenly can become feasible. So it has to be done accurately, and it's not based on any strong assumptions. It could be based on data readily available, which includes well test data, and the near wellbore model will definitely be built up to match the well test behavior. So the answer is why is, well, because it can really make your design more efficient and improves the chances of HIPPS success. Okay.
It looks like the Q&A panel is not working for some people. Maybe if participants could use the chat box to post any questions you may have. In the interim, another question for you that I'm able to see is, does the misrepresentation of pressure buildup in the reservoir after affects other aspects of flow assurance design?
Oh yeah, many. And I've been really fascinated at how we've got away with such a old assumption, which is an instantaneous pressure response to flow changes. But there's many other topics where this is going to impact. Definitely in slugging, as we saw, other than HIPPS design. It can also be, I've seen preparing operating procedures and you have well integrity concerns, and then we're telling the operation people based on our Olga simulation, hey, you can only ramp down, 3,000 barrels in 1 hour when they could actually do that much faster. So, we are being way too conservative when we looked at the drawdown variation of the wellbore pressure. So that's another thing. Others could be even JT cooling through the choke. We might be depleting the pressure way too fast. So instead of having a few minutes of chilly choke, you may have a few hours, and then that can be a concern. There are many aspects where the difference in pressure response in the wellbore will have massive implication in everything we do in flow assurance. Yeah.
Good. Another question: how are you handling the near wellbore model?
So, that's it. It's resulted from a lot of thought, and it's basically we're internally using Olga devices to create exactly the behavior you would expect from the solution of that partial differential equation. So we have basically in tools within the Olga framework which reproduce the behavior, and these are surprisingly fast to run and surprisingly accurate. Yeah.
I think we're down to maybe the last question here. Just let me see. No, it doesn't look like it's coming through.
Okay.
Okay. Oh, no, here it comes. Have you applied this to systems where slugging was not predicted for the well model versus field? Or, yep.
Yes, and it's been the difference between slugging and not slugging. The slugging one, I mean, the first thing you need to check is, do we have pressure drop through the choke, the wellhead choke? If you have enough pressure drop, this really doesn't matter much. But if you're in a fairly depleted field where you're minimizing pressure drops through those wellhead chokes, you're going to have a big connection between your pipeline and your reservoir. And I've seen firsthand how increasing the compressibility is the unique difference between predicting slugs and not predicting slugs. And sometimes I've seen those, let's see what LetterFlow says, let's see what Olga says. And what I know is this is not a LetterFlow Olga issue, it's actually a compressibility issue, and you're not capturing the full compressibility of your system. And once you do, you start seeing those slugging behaviors. Yeah.
Another question, you will have to have full trust in the wellbore properties to accurately represent the pressurization time. How can you count for changes over life of field?
Well, that's one thing that I want to make clear. We don't have a reservoir model. This is an idealized model, but captures enough of the wellbore dynamics for the short-term transient. We're not going to be telling you how your PI is going to evolve because of water saturation changes or rock compression, or we're not going to be doing wellbore spacing with this. We're not going to tell you forecast. We're going to ask for the same input we ask in flow assurance projects. Reservoir gave us a reservoir pressure, gave us a PI. Maybe we're going to look at the completion schematic to kind of understand more or less the pay zone thickness, and looking at the entire volumes recovered. And that's enough to capture a transient for those short-term transients we modeled. Then short-term, again, for us, that might mean even 24 hours is still very short-term for a reservoir time scale, okay? So it's not a reservoir model. You would never be able to get all the nuances you need to get to do proper reservoir analysis, but it definitely greatly improves from our current steady state IPR assumption. So the accuracy, we have that data reliably. That's the PI data. It's as reliable as your PI data. And we're just interpreting further that PI data within a specific framework. and has to be validated with well test data, which is something we've internally done. Okay.
Next question: to what extent has this method been tested against operational data, since the difference between methods in the Olga modeling example is very big?
That's a work we're wanting to start, especially with operating companies that have this operating data. So it has been mostly tested in the literature. It has been tested not with the working near wellbore model that we currently have established at EvoLeap, but with changes in compressibility. So for instance, I'm trying to match production data for a previous client a few years ago, and I noticed their wellbore chokes were fully opened, and when you included additional volume, you started to reproduce the field behavior very closely. So we didn't use the current wellbore tool we have, but the increase on compressibility was definitely the difference. So it's one of the works we are very interested in, which is collaborating with existing operating data and then proving this concept and basically improving everybody's workflow for wellbore slugging prediction.
We have a lot more questions, David, as the technology started working. So the next question is, how do we know we are not overly optimistic with the transient approach in terms of the results?
Well,
and second part is, how are the simulation times affected with the transient approach?
Yeah, the first part of the question is, you will have to use some margin, and this is HIPPS topic is a bit of a tricky one because it all comes down to a regulator, right? And if our engineers are having the slightest doubt about it, imagine the regulator. So it's basically, it requires some study and some judicious margins, I believe. So yeah, it could be overly optimistic. You tell, we need 45 minutes, but perhaps even if you take a 90% margin or so, you still come down to much better reaction time than you would get if you assume that the reservoir reacts instantly. Okay. And then I think it would be a matter of, whenever these fields are developed, there's always a well test. And it's really a matter of showing that your near wellbore Olga model is reliably capturing the well test behavior. Yeah. And then how it affects the simulation time, it doesn't affect it, basically. It's the same as having the IPR. So it's really cool. We're actually very excited about this.
Next question is, what is the main difference in terms of the input data between the steady state IPR and the transient IPR?
Yeah, the transient IPR needs to have basically a estimated expanding volume. Okay, that's the missing key. So the PI is fudging the permeability, the in situ viscosity, and the pay zone thickness. So you need to have also kind of the entire drainage volume, and that we found a few clever ways to get estimated based on the production profile, and then you have also the pay zone thickness, and there's also you can get fairly good estimates from the well log data and or the completion schematic. And in our fairly high level data on these two specific conditions I told you are actually enough to get accurate. If you look at the pressure profile during our slugging, even the slugging simulations, the really what gets impacted. Oh, I have an issue with it. But what gets impacted is let's say this is the wellbore. It doesn't travel too deep into the formation, so actually that overall drainage volume and the pay zone thickness, it really only has an impact on the very near wellbore. So you don't need to be awfully accurate to get an accurate transient response to those fast transients. Yeah.
Next question. How are you addressing compressibility and fluid behavior, mass transfer between phases during pressurizing?
So in this scenario, everything is handled by the simulator itself, by Olga. So we have, you might have a compositional tracking model or a tab file, depending on your needs. So that's basically resolved within Olga itself. And to be clear, the near wellbore model we've developed has been for single phase or at least liquid flow in the porous media. Multi-phase hasn't been addressed. However, subsea, deep water, I have yet to see completion bottom hole pressure below bubble point for oil system. Of course, if you have condensate or gas system, it's the case. But this is more applicable for oil development for now. But we do see a potentials to expand it to even multi-phase. So basically that's all solved within Olga itself. Everything we do it's included within the Olga, and mass conservation and per phase conservation is ensured by the Olga framework.
What is the difference in terms of simulation time between the two approaches?
It's almost none. It's almost the same simulation time. It adds a few complexities, but the way we have it set up, it's really not changing much. We haven't quantified it, but it's not doubling your simulation time. I don't think it's increasing it by more than 20%.
I'm waiting for some Q&A questions to reload. Another question: does the misrepresentation of pressure buildup in the reservoir affect other aspects of flow assurance design?
I think we had that question before.
You did? Okay, some of them are getting reposted in the Q&A, I think.
No worries.
Okay, another question: how do you match Evoleap's approach to the actual performance of the reservoir? Do you have to tune to field data, or can you take reservoir parameters, permeability, etc., and match IPR and buildup?
So the example you saw, we just assumed permeability, drainage volume, porosity, and we have of course the fluid properties, and it resulted from that. So in reality you would be able to also tune it to the well test data, but it's not tuning completely overhauling your model. It's just basically adjusting small parts of your near wellbore model such that you match the well test behavior. So even though the report may say your permeability is 50 millidarcy, perhaps we find that with 30 millidarcy you better match, and we also can have multiple permeabilities, so there's definitely a lot of potential tuning with the wellbore data, but nothing, these can also be done at a conceptual level and should also produce predictive behaviors of that near wellbore fast transients. Not for the long-term reservoir, this is not a reservoir simulator, but for how the reservoir would behave given fast impulses from the wellbore. Yeah. Hello. Can you hear me, Ayn?
Yes, sorry. The question was, and this will be our last question for the session: in most HIPPS design cases, it is depacking, fast depressurization from peak pressure that defines the HIPPS sizing scenario. Is this tool applicable for such cases?
Yes. I have been in a project where the depacking was the sizing case, and that's accurate. You know, and then it comes into the hand waving theory. I mean, if you're depacking with a choke, the choke has a very small CV, so then you know what's that critical flow from that choke opening, and how what's the fastest you can open your wellhead choke? You know, it might or may not be, but when it is, this tool is also applicable. I've seen certain operators assume a constant pressure boundary at the bottom hole. That's also extremely conservative. That, you know, you assume constant reservoir pressure at the bottom hole. So depending on what your system is and what the volumes, the relative volumes of your pipeline and your wellbore and your reservoir, it may or may not make a difference. Okay, applying this method for that specific design. But for instance, if it can be, for instance, that your bottom hole pressure drops below that reservoir pressure, and that drop will give you added time to react when compared to the, you know, just assuming you have a constant reservoir pressure there. So it's true. The depacking could be the sizing case, depending on, you know, safety standards and whatnot. It often is, and the impact of this tool would be different for that scenario.
Thank you, David. We have other questions, but limited time left as we wrap this up. So we will get back to you with answers to those questions. And please do reach out to David or myself with any questions and further discussion. With that, I'd like to thank you for attending the webinar. As mentioned before, the recording will be made available to you on our website shortly. And please keep an eye out for future EVELEAP webinars. Thanks again.